All right. Yeah. Good morning. Hello, everyone. Today we're going to do a little bit of an introduction into semantic entity matching. This is taught by Harshad and me. I'm going to give a little bit of an overview of the area to give you a bit of a feeling of why we need it and a bit of the context. And then, so we divide it into like 2 bits. So I will be doing the first 30 minutes. And Harshad will do the second 30 minutes. All of this, what we are talking about, is also documented as a self-taught course in OBOOK, and I've already linked it in the Monarch course list as well, so you should be able to find it if you want to go over this, and of course you will get the recording. But because there are so many pictures today, I'm using a slide deck, which makes it a little bit easier to communicate. All right, so basically, just to establish a context, let's think about a scenario where we have a bunch of organizations that generate data in some way. So here, this is just like 4 kinds of organizations. That have their own internal databases, their own internal data models, and whatnot. And then eventually the day comes that these organizations realize that it makes sense to try and standardize their data, maybe in response to a nation-wide verification effort, or in response to the needs of an organization to integrate data internally. So, for example, the EBI introduced the experimental factor ontology primarily also as a means to integrate data inside of this huge data generating organization and link these databases internally together. And they will then say, okay, now is maybe the day where we need to kind of bring a bit of standardization into our data. And so what happens is because the world doesn't have like a single top-down standards body that can affect everything, it's usually that standardization is more like a kind of decentralized situation where you have a bunch of organizations. By the way, I think I hear some clicking and typing noises in the background. Just if whoever this is could mute themselves. So these organizations are, for example, these 2 here, these organizations may know each other or may by chance decide to adopt Uberon to describe, for example, their anatomical data, for example, in the context of gene expression databases or whatever. And they basically go through all of this hard work of replacing their maybe originally just manual strings-based curations with controlled vocabulary terms from something like Uberon. Yeah, you all know about this very well, so I'm not going to go into much detail here more. But on the other side of the globe, this organization down in the left corner will say, for describing our data, we have this great standard called the Foundational Model of Anatomy, and they start standardizing their data to that. And maybe there's a third organization that has never heard of FMA, never heard of Uberon, or for some reason doesn't think it's entirely suitable to the use case, and they go ahead and develop their own ontology to describe their anatomy-related data. All right, so as many of you here know very well, it is already extremely difficult to adopt the standard, but it is even very, very hard to continue curating to it, because as uptake is changing, so we have something like Uberon, where many different organizations are involved, lots of different opinions start slotting in. Let's say one organization, this is a fictional example here, but one organization says, oh, I really need these 200 terms here for my curation efforts, and another organization says these terms are completely out of scope for Uberon, they shouldn't be there. And because it's a species-independent ontology, you even have like fights about like how should which exact anatomical entity be classified. So there's a lot of like cost in even bending your own way of working towards the standard. So adopting a standard, keep using it, means also giving up a little bit of the original flexibility that you had when you were completely free to do whatever you wanted. So what does this mean now is that in this scenario where you have these different semantic spaces, as we call it, emerging, where, you know, different kind of places in the world started adopting different semantic standards. And this is not just ontologies. This could be even something like adopting LinkML, for example, or adopting phenopackets for sharing stuff. If they will all start and say, okay, this was a lot of work, and when now someone like a smart ass like me or other people in my domain comes along and says, well, eventually one of these standards will emerge as the superior one. Obviously, this is Uberon in this case here, and everyone will see the light and will converge on the standard. Then we have a new thing coming. This is not going to happen. These organizations, these places here in the world, they have done so much work to standardize their data that there is no world in which they will agree to then go through the bent over backwards process of doing the same thing again with a new standard and paying this cost again, or at least in many cases, this won't happen. So there will be some that will be able to be, you will be able to convince if the standards are reasonably similar, but in many cases, this just won't happen. All right. So why do we care about stuff like that? This is just a simple example for that many of you should be familiar with from Monarch Initiative, where we try to do something very, very simple sounding. We just wanted to know how many rare diseases are there. But if you look at the various different semantic spaces, or the kind of resources, databases, and so on that are dealing with rare diseases that are scattered across the world, one thing that we realized back then is that only a tiny fraction of the rare diseases in that have been documented are actually documented in all of the major resources that we were looking at. So in this case, we were looking at NCRT, DO, GARD, Orphanet, and OMIM. So just a tiny fraction was in all of them. And actually, many of these, the rare disease concept, were only found in a single resource. So there's a great need of being able to reliably count across different resources, and to be able to count, you need to know which concepts correspond exactly to another. And of course, for us here in Monarch, it is super relevant as a use case to be able to bring all of these resources together for more advanced analytics, not just counting, but also be able to do things like, let's say, semantic similarity comparisons, being able to compare phenotypes and groups of phenotypes and all this kind of stuff. Yeah, so this is an example picture from some work that we did with the Critical Path Institute, where we linked some of Monarch data, Monarch ontologies, in particular Mondo, to some registry, rare disease registry data. And here, in these kinds of cases, you really want to make sure that whatever information you pull in from external resources, if they talk about Friedreich's ataxia, for example, you really want to make sure that there's just a single bubble in your knowledge graph that represents Friedreich's ataxia, not 10 different bubbles, so that you can appropriately aggregate and unify the all of the information and make it useful for semantic similarity comparisons. And for that, again, you do need very precise mappings. So we are left with this kind of state, different semantic spaces. Semantic web won't happen where everyone is using the same space. So the reality is we need, in order to shift data from across these spaces, we need to be able to map between these standards that are being used for annotation. All right, so what exactly do we mean? Just for Sarah, if you see anyone asking a question in the chat, just encourage them to interrupt me immediately. There's no need to wait. So so what exactly is then an entity mapping? So entity mapping is like a word that maybe many people haven't heard so much, because you've heard words like knowledge graph matching or ontology matching or ontology mapping or term identifier mapping or value set mapping, or and so on and so on. Maybe entity mapping is a word that you haven't heard that much, but entity mapping in its raw form, what we mean by this is, let's say you have a case where in one, let's say, relational database about rare disease, you refer to a disease using the string Friedreich's ataxia. And in another database, let's say this Excel spreadsheet here on the right, you refer to the Friedreich's ataxia using this OMOP 441554 identifier. So the core is that both of these symbols, so call them strings or whatever, are supposed to refer to the same real world thing, so the disease of Friedreich's ataxia. So symbols could be anything from a code in a terminology, a class in an ontology, an enum in a data model, a value in a value set, a string in a text field, and so on and so on, just to get a sense of like this idea of what an entity is in this sense. There are different kinds of entity mappings we talk about. So we have entity mappings between strings and let's say ontology identifiers or any kind of identifiers. We have identifier to identifier mappings, and it's really important here to remember that we are not only talking about ontology identifiers here. Yeah? So many of you are handling mappings between genes, for example. They are not necessarily ontological. These are database identifiers in HGNC and Ensemble, for example, that are being mapped together. This doesn't matter. These are all different entities that are being mapped together. And there are complex mappings, like, for example, cheese sandwich being mapped to two different terms like sandwich and cheese. So what's the problem? So we have the situation, we have different spaces. This is not restricted to anatomy. Obviously, we've said, for example, you can imagine there are many different places in the world that are using different disease ontologies, different gene identifier schemes and whatnot, and all of these form different semantic spaces, and they need to be linked to each other. And what this means is that the mapping space can get really, really large. So if you look at the right side here, in the worst case, you have to map, let's say these are just 6, let's say, semantic spaces that we try to map to each other, and they can easily be, you can easily imagine many more. And the number of kind of mappings you need to consider from C1 to C3, from C1 to C5, from C5 to C1, also backwards, everything in all directions, is nearly n squared number of mappings. So there's lots of combinations that you need to consider when you map between these semantic spaces. And let's say you do that in practice and you generate all of these mappings, then in reality and in practice, all of these also start becoming conflicting with each other, and you need to understand how to deal with this. So it's a really difficult problem that you have such a huge space to deal with. And then now, okay, over time, some people try to mitigate this problem by introducing hub and spoke solutions. So which means that rather than trying to map all of these resources crosswise to each other, you create one internal concept like Mondo does, like let's say Friedreich's ataxia, and then you just map all of the other resources that are talking about Friedreich's ataxia into the one single resource in the middle, and don't really look at kind of how these things map between each other. But even these kinds of solutions are slowly proliferating as well. So what we do to try and mitigate the situation is we are trying to build automated matching pipeline that allow this kind of situation to scale, because obviously a complex mapping scenario like this here, it's going to be nearly impossible or impossible to have humans go and do all of these mapping by hand. So what we try to do is we try to build tools that allow us to automate some of this stuff. So the goal here is to integrate two semantic spaces by computing semantic links between these spaces. So you have, let's say, these two spaces up here. These could be ontologies, databases, and so on. Then you have some form of matching algorithm. And then when this matching comes out, you get the links between the appropriate nodes, merge this thing together, and then you can use it in a merged scenario. But the problem, obviously, there's a wide variety of different ways to express the same thing. There's a lots of variety of the way that, for example, labels are constructed, even in controlled terminology. The slide is actually used to describe something else, but I just want to give you a sense that there's so many different ways to, for example, express that a sample that you have been working on is pertaining to a female organism or something like that, that you can easily imagine, like if you have to kind of match somehow across things like that, this is going to be really, really not so trivial as it might sound. And similarly, if you are in the value set business, sometimes there's nothing lexical to go on at all. Like here, you have a value set mapping where you have like a bunch of codes from that are very specific subgroups of Alaska natives, like Haida and Huna, and then you have to map this to a different code set somewhere else that just has like one single class to map to, and there's no automated way to do that. So actually a human will have to go in here and deal with this manually. Just make sure that, yeah, I'm well in time. It's good. And similarly, just some more examples. So this is an example from OMOP, which has lots of different mappings that stored between terminologies like ICD-10 and OMOP standard concepts. And you can see, just by the lexical variation that there is, that it's going to be really hard to just, if you're assuming something like a lexical matching approach, which is what most people are thinking about first, and what we are going to show you how to do also today, you will see that this is going to be non-trivial to get a program to find a corresponding match between this amoebiasis and amoebic infection, or some of the other ones here, like pedestrian on roller skate injured in collision with pedal cycle and traffic accident, to these, let's say, other complex ontology concepts. So we need to sort of link between those, but it is going to be super, super hard to do this automatically. So this is another example we sometimes use in Monarch presentations, where you can see, like, you go there with the assumption that at least if you are using the same label, you may be talking about the same construct in the same context. So here you see that, for example, in 3 ontologies, Ordo, in Orphanet and NCIT and the disease ontology, you see the same sounding disease, Zellweger syndrome, being classified very differently from in all of these ontologies. So, and now if you also take into account that the definitions will look quite different about these diseases, then you have to ask yourself, like, how can I really reliably map these two things together, and do they really mean the same thing? So it's another big question mark for the automated matchers. Okay, so lexical matching would have a really hard time distinguishing exact from non-exact matches. So we've hinted at some of these examples before, but this is also another site that we show quite often in Monarch. You can have situations like Fanconi anemia being in GARD being linked to Fanconi anemia B in OMIM. So again, as a reminder, we in order to merge our knowledge graph, to count how many diseases there are, we need to know, are these things exact or are these things broad or narrow? And there are many different ways in which they can be related. They can be broad matches, they can be narrow matches. And in reality, there can be even matches across different analogous concepts, like, for example, a mapping between the absent thumb phenotype and the Fanconi anemia A disease. So this is then we are getting into a really complex space for what exactly and how these mappings are related to each other. And to all of these things, we, as, let's say, people that are trying to generate mappings, we need to be really sensitive towards. All right, so we're nearing the end now for the basic introduction, but I just want to point out for those of you that are not so familiar with like the area of ontology matching, there are so many different areas that are really culturally very disconnected, I would say, from the review that I tried to make over the last month. But there are so many overlapping kind of concerns, like, for example, the areas of ontology matching, clinical terminology mapping, value set mapping, knowledge graph matching, thesaurus building, so determining synonyms for concepts, named entity recognition, entity linking, which is the kind of toolkits for taking in, let's say, a free text like a PubMed abstract, identifying a string in the PubMed abstract that like Friedrich ataxia or something like that, and then determining which ontology concept or knowledge graph concept this belongs to. Entity resolution and record linkage, which is like a huge, probably the biggest of all these here areas, which is concerned with figuring out whether two database rows correspond to the same thing. And schema matching, of course, which is trying to figure out, given two schemas, which parts of it, which elements of the schema are linked to each other, and how can we translate between the two. But while all of these have completely different use cases and the exact nature of what we do with these mappings may be different, there is like a unifying core underneath all of these. And this core is usually, so in basically all of these approaches, you use some kind of common tooling around lexical matching. So you want to figure out some mapping candidates across these spaces by doing by, for example, looking at labels and figuring out whether two things have the same labels, and then hoping that this is sort of a good mapping candidate that then you can pass on to a human curator to verify. Or you want to use semantic similarity-based matching, whether this is something like structural over the graph using normal graph similarity, or whether this is based on even some more advanced graph embedding-based similarity approaches. These can also help us to find good mapping candidates. And also the structure of the mappings that come out of these kinds of processes, all of these sort of look similar, having an entity on the one side, an entity on the other, and an arrow between the two, and often even similar metadata, like what's the confidence for this mapping, and so on. All right, so this just to set the scene a little bit. So we will talk a bit more about more details in lexical and also semantic matching in a future tutorial. But today we are going to show you how to do lexical matching with Oak, and give you a bit of a sense of the kind of thought processes you want to go through when you are building your own matching pipelines for your own, let's say, mapping project. So with that, I'm just going to stop sharing and hand over to Harshad, unless there's any questions for the part so far. I didn't see anything in the chat, so I'm just going to stop sharing.
Thanks, Nico. Let me share my screen real quick here. You guys see my screen?
Excellent. Yeah, I can see it, and it's a very nice font size. I think I can see everything very clear. Thanks.
Perfect. Okay, so just for reference, this is the tutorial that I'll be following if you want to follow along with me. So as Nico explained, this demo is for lexical matching. And the prerequisites for this tutorial is that you're aware what robot is and what SOM is. SOM stands for Simple Standard for Sharing Ontology Mappings. In this tutorial, I'll be using a new tool called Oak. It stands for Ontology Access Kit, which was developed by Chris Mungle. And right now, I'm going to use two different ontologies, Foodon and Wikidata. And in the interest of time, I'm just going to use subsets of those two ontologies so that we could get to the results quickly. For that, the subset would be basically fruit juices. So the first step, there are two ways to do this. One, you can actually install oklib locally and set it up and run it. And since this is an ODK tutorial, I'll be using the ODK Docker image. So all of my commands will be prefixed by shodk.sh. So firstly, we get the owl file for foodon using the persistent URL. It should be fairly quick. And as this is going on, I'm going to talk about getting a subset from the foodon ontology. So I use robot in this case. We extract using the myriad method. The input file is the file that we just downloaded. The upper term is the query or the ID for the fruit juice food product label. So let me just copy paste this, and I'll go through each parameter separately. So here we extract using the myriad method with the input of foodon.owl, which we just downloaded. The upper term is the fruit juice food product ID. Lower terms I'm using for apple juice, orange juice, and grapefruit juice. Those are the three IDs that you see under lower term here. I export this output to fruit juice foodon.owl. Fruit juice food foodon.owl. So this should not take a whole lot of time. So while this is going on, the next step would be using oak to get the descendants of the juice ID. For -p stands for predicate, and we're using is-a and part of predicates. And the output would be a TTL file, and the small o stands for the file name, and the big O stands for the format of the output. So let's run this. This should take around 30 to 45 seconds. And as a next step, once this turtle file is generated, we will convert it into an owl file using robot, as you see here.
You were probably blocked from Wikidata, but don't worry.
So let's see. Let's run this. And if not, I have a file already in place. Yeah. So I already have a file here. Trust me, it works.
No. This is very likely that you've just worked on it a lot, and they have just blocked your IP address for temporarily here. So I think that's just what probably happened.
Yeah. So this basically is the file that gets generated. Next, we convert it into an owl file. Here, see the owl file generated. As the next step, we will merge the two files, which is the owl file, which we got from Wikidata, and the subset from foodon.owl, which is this file here. So you merge it using robot. This is the command for that. So now the actual matching process or the mapping process is done using this command here. So for using oak, we use the lexmatch command that basically does the mapping between those two subsets from Wikidata and Foodon, which had been merged using OWL. In this case, we're using the SQLite implementation. There are other implementations that are offered by Oak, but we're using SQLite. So what this does is it converts this OWL file into a SQLite database and then queries it to perform the lexmatch operation on it. It's slightly quicker, and that's why we're using SQLite. You can experiment with other implementations as well, but it might take a little longer than SQLite. So this is like a vanilla lexmatch. We're not adding any other configuration file or anything to do the matching. So if you see the output here, so this is similar to the SOM output. And you see that subject ID for Foodon, subject label apple juice, it's like a string match that has happened where the subject, predicate, and object, as you see here, is apple juice, and the IDs correspond to the two ontologies that we just merged. It also gives you a confidence of half, which is default, because there aren't any rules that are added to it, and by default, it gets assigned a close match predicate to it. Yeah, and as a next step, we will be introducing some rules for the lexmatch, for the lexical matching, and this is what it looks like. This is a synonymizer pre-processing step that we do before the lexmatch occurs, where you remove parentheses. If the labels contain parentheses, it drops it, and the entire string is considered to be the label, and then it looks for a match in the other part of the DB file or the SQLite database file to see if we can find matches that way. So let's run it. It's exactly the same. The only addition is the rules.yaml file that I just showed. Let me run that real quick. So it generated this file. Again, it starts with a query map, and these are the column names. And now you see that there are labels with parentheses in them that are also matched to labels that don't have it, but match exactly with the other one, which had parentheses, just ignoring the parentheses part of it, but it says that there is a match between the two. And also we get more matches than before. Towards the end, you see a must, which was in the previous match as well. Initially, I thought it was just a verb, but must in the juice world apparently is a mixture of juice, pulp, and the crushed seeds when you create the juice. So that's something that I learned during this demo process. As you see here, the matching has been done, but still it requires manual intervention because, for example, here, unpasteurized in parentheses for orange juice, it's hard to say that it's an exact match for orange juice. And so it still requires some manual intervention or addition of more rules in the rules YAML file to fine tune it and make it a little more accurate. And that's basically the tutorial that I have. Any questions?
Harshad, so can you explain the matcher rules file maybe a bit more detail, and then we can let Sierra ask her question, and maybe we start with her question in terms sorry, Sierra, you can ask your question here.
Oh, sorry, I just wanted to know if it removes the parentheses and the content of the parentheses during the match, or just the parentheses themselves.
Just the parentheses. Yeah, it
Okay,
just drops the parentheses and considers the entire label with all the text in it. So in this case, it'll be orange juice liquid without the parentheses. You consider that whole label.
So when it says orange juice unpasteurized, if you, it matched just orange juice on that?
It matched orange juice being a part of this entire string of orange juice unpasteurized.
Okay.
So yes, only orange juice is matched.
Yeah, it
So if you
matched
go back
only
to the matcher rules, just maybe explain how this like regular expression system works with synonymizer.
Sure. So basically what this is the explanation of the rules text, but it is a regular expression which looks for any actually, so it looks for anything within brackets and drops it. So the replacement is that. So here you're right. I misspoke. I'm sorry. So when this is considered for the Lex match process, the part in the parentheses is dropped. And hence what remains is what is used to match this. So the idea is temporarily we ignore what is in the parentheses and look at the core label of what it represents to do Lex match. And hence I said if there was any important information, that's when the manual intervention comes into place to verify if that the mapping that has been done is accurate or not, because all this does is basically brings to focus that there is a match, a potential match between these two ontologies, and the manual intervention basically confirms or denies it.
Okay, and so those rules that you make are they're project by project based on
Yes.
your knowledge of the ontology. Okay.
And this is a very, very great question, and I want to really emphasize that that this question is a question that you should always ask yourself also when you are designing your own rules. So these rules are very often not transferable, as you can see here with the unpasteurized. Yeah, so it may not be the case that in your domain you can just drop the stuff between label without losing significant information about the entities. And when we did our Mondo work, for example, we knew that what was in brackets, what was actually the identifier of the class, which is basically redundant with the whole label. So we could safely remove this without changing the meaning in any way. But in this case here, I would be very careful for this particular example that Harsha just presented. I would be very careful for adding a rule like that, because it seems that in most of the cases, actually, what is in brackets is very relevant to the semantics of the concept, and I wouldn't just, drop it. But this is just for illustration to understand that you can and that you can do this. Okay. So yeah, I interrupted someone that wanted to ask something.
No, this is fine. It's a follow-up question. So, in this case, in this case, the match between orange juice and pasteurized is so orange juice and pasteurized is an exact match to orange juice. So, I guess I have 5 questions related to that. Number one. Can you say that it might not be exact just because we dropped something unpasteurized, that we dropped unpasteurized, and that's how you made that match? So it's, even though the text is exact, this something else. So maybe it's not exact. And, second question is, would that be something that you can set, let's say, maybe in the confidence code? And how do you decide the confidence code? Like, how do you set it up? I think it's like 5 questions in one. Yeah. Hopefully that makes sense.
Yeah. So the confidence is something that is set based on. So there are also other rules that we've implemented here. For example, subject match field, if it is either an exact synonym, an RDFS label, or a preferred label, and an object match with the same, it gives a weight of 2.0. Now, I don't know the exact math that goes behind it, but the weight is what decides the confidence down the line. That is something Chris might be in a better position to answer. I'm not sure if he's in this call, but having said that, in the rules itself, you can also, based on the weight, you can also add like a weight parameter here saying that, okay, this could be not just weight, even the predicate ID. You can replace the predicate ID saying that this could either be so and so match or so much weight. Based on the weight, the confidence can be assigned. So again, this is still the initial stages, and we can do a lot of tweaking to actually make it more accurate. And as I said, this is just a bare bone demonstration that I'm showing. But yes, you're right. This can be matched. This can be manipulated in the configuration itself to have a general definition such that the results show something close to what you would expect.
Okay, great.
Did you want to go? Did you want to ask something to that end, Sierra? Otherwise, I wanted to say something about that question.
Go ahead. Go ahead.
Yeah. So I think that one really important thing to remember is that for our purposes right now, Lex Match is really a very simple tool. There are much more sophisticated systems out there for doing lexical matching with many more pre-processing steps and so on. So this is not an invitation to say, use the great Lex Match. This is an invitation to think about lexical matching in a way that you understand that you should be thinking very carefully about defining your matching rules, that you need to iterate and tune the way that your automated processes work by curating these matching rules. And in particular, so I think that two things that you've asked, Sabrina, are actually not possible. So one thing that you asked is, can you say that if it was a match based on a removal of a part of the word, can we say that this is a broad match? This is, for example, right now not possible, but obviously it would be very relevant for many use cases to be able to do that. But that's not, so Lex Match is not so much a kind of full-blown matching tool. This is really more for us an educational tool, and also a tool for generating fine-grained, very reliable lexical matches that can be reviewed easily because they have nice metadata from SESAM attached with it, which all of the other lexical matching tools won't give you. So that's kind of like what this, where the design space of this is. It's much more trivial than most other lexical matching tools out there. And regards to the weight, actually, just another quick word is, so if you go back to the matcher rules, Harshad, so the way that these weights work is that these weights add basically cumulatively evidence to the fact that if there is a match based on an exact match based on, let's say, a subject exact synonym and or label to a narrow synonym on the left side, then there is a very strong evidence, like with a weight of 2, that this corresponds to a narrow match. Now, if you had like strong evidence towards some other kind of match, that could be this would lead to a higher confidence, for example, and you could easily weed it out by querying for all the mappings with the highest confidence using, for example, SESAM toolkit or something like that. So the weight is an open-ended way to say, I trust this rule is really giving me a lot of confidence that if that's true, then I can assert that this is an exact match.
Okay, thank you. And you just decide whatever weight it is. It's a, I would say, a personal decision.
It's a personal decision. Yeah. You can. It's actually not a value between 0 and 1. It's like an open-ended value to. You can add any kind of confidence to it.
Great, thank you.
All right. Sierra?
Yeah, I really appreciate that answer. So it kind of makes me wonder if I should actually ask this question. It might be too far upstream, but you guys are both really smart, so I'm going to ask it anyway. But how do you make a matching rule when you can't see the entire content of the 2 files you're trying to map together? right? So if I had a particular synonym that did have parentheses and it had unpasteurized, and I looked through the first 50 lines of that and I said, well, you know, I think I can probably replace what's inside the parentheses with nothing and I still want to get the match. But then down at the bottom of the file, there's, you know, a bunch more with really specific content inside the parentheses. How do I, you know, make a matching rule without knowing the entire contents of every line? Or do you just basically make a matching rule and then have an expert sort of review the entire thing? Or or is there like a statistics calculation that you do? Like this is how many things matched without the parentheses, and this is how many matched with the parentheses? Or like, what's the upstream processing that you do? Or is that sort of an inappropriate question for this demo?
It's very appropriate, and Harshad and I are constantly fighting with this question. So I will try to, so I will say it like I think currently see it, and I guess that there is probably better ways to think about it. But so Harsh and I have this like massive problem with trying to align, let's say, huge clinical terminologies with each other that have widely divergent labels and structure. So we have always kind of like a very fine line that we need to tread between increasing the recall of the mapping candidate generation, so getting more matches generated on the one side, but on the other side, also keeping the number of false positive matches down. And we always think of it as and that's also what you will see when you read the tutorial proper, we always perceive of the outcome of a matching process not as a mapping, but as a mapping candidate. So we never perceive the outcome of a matching as a mapping. So what we generate is we generate candidates, and these candidates can be verified in various different ways, like for example by a human curator, which is what we do in Mondo most of the time, but they can also be partially verified by other tools, like for example automated reconciliation tools like Boomer, where you can at least weed out some of the false positives. But the general thinking is always like you have to introduce a process for false. So if you have a project that requires matching, you have to introduce a process for false positive review, which is basically check that the matches don't contain any wrong things in it. And what we do, Harshad at Dice, is basically we produce these candidate matches. Sabrina will look at them and say, this one is bad, this one is good. Then we sit down again and think like, these bad ones, could we have avoided them with a smart matching rule somehow? Then we design a matching rule to avoid them, and then next time they don't come back. So that's kind of like the process for false positive review, but we also always need a false negative review, which means you need to figure out how can you make sure that you get all of the matches that are correct out of the system. And we have this other process, which is a bit more honky, but it still works somehow, where so what Harshad does is he takes, let's say, all of the human curated mappings we already have. Then we look basically at the ones that the automated process does not find. So we output like lists and chunks of mappings that cannot be detected by an automated approach, and then we go again. Could we have done something to catch this mapping? For example, this is how we figured out that we should remove the brackets from ICD-10. Could we have done something? Then we iterate again. Whatever we do, in the end, when you design a matching process, it's always going to be a heuristic. It's never going to be complete, and it's always going to be faulty. And what you need to decide basically for yourself at the end of this process is, for your use case, how much noise tolerant are you? So do you have, let's say, are you Harry or Justin and build like a big machine learning prediction thing? Then you are very much more fault tolerant. Let's say you can accept, let's say, 5% bad mappings in your data, while if you are, I don't know, building a clinical system that tells clinicians, kill this patient or give him this medicine or that medicine, then you don't have any room for error. And in this case, you really need to go into every single mapping and have it being verified by a human reviewer.
That makes a lot of sense. After doing this with a couple of different sources, have you found that there are very generic rules that could be a starting point for somebody wanting to do this mapping, or is it very individual based on every single mapping, and you have to kind of like balance how much time you want to spend versus how much you can just do manually?
I'm
You always
thinking
say,
I think that it's very there. So let's say it like this. There are so, and you can look at this actually very nicely in I can show you quickly, because we have started documenting these in the semantic oops, that's the configuration, semantic mapping vocabulary. So there are a few what we call, so, and there's where we are distinguishing a little bit between the rules and the pre-processing. Yeah, so there are a few pre-processing rules that are pretty standard, like for example stemming, stop word removal.
that's great. That's perfect.
And
that's what I was looking for. Yeah.
And case normalization, you know, uppercasing, lowercasing, diacritic suppression, blank space normalization, links stripping, digit suppression. That's actually a very faulty one here. For us, we should never use it. Punctuation elimination and all this kind of stuff. So there are some standard documented pre-processing techniques for these algorithms. You can look at a good list in for example, the ontology matching book, which is basically my Bible for this kind of stuff. It's really pretty awesome. It's old, but pretty awesome resource that can be applied. But when it comes to this tableau that Harshad was shown, this regular expression replacement type work, I think that there's very little that you can do without knowing the domain. You need to play a bit, and I personally prefer to be a bit like, you know, start very conservatively and then build up on top of conservative approaches. And yeah, and I think that what we need to do next is actually import, and I was just having a conversation with someone about this, to actually use some even more crazy things like GPT-3 to get some better suggestions in and see whether these things can actually, you know, increase the recall without harming the precision too much for this kind of mapping candidate generation.
Thanks. That's perfect. Thank you.
Any was any other question out there? All right. So I just wanted to quickly show all of the stuff that we've talked about that I've talked about in the beginning can be found in this overview here as well, with some additional tutorials for those that are interested to go more into depth. I think I wanted to show one last picture before we close. So this here is like a sort of idealized image of an automated matching pipeline as you would build it, let's say, when you were building it. So you have the way that this works is you have on the side here, let's say you have two resources you need to align, two or more resources. What you first do is you go and figure out whether there is already any resource out there that shares these things, shares the mappings between these resources. You import those. Then you use matchers like the ones that we've discussed today to generate what we call a seed mapping. So a seed mapping is like a starting point mapping, let's say. And then you embark on like an iterative process of refining those mappings over time. And these mappings typically are divided into three buckets. One is the anchor mappings, or the true positive mappings, which are the mappings that are verified to be correct, like, for example, the ones we have in Mondo. Then we have the overestimation mappings, which we called today the mapping candidates. So these are all the mappings generated by the matchers but haven't been reviewed yet. And then there is a file that is negative mappings, which are those that have been caught by the automated tools but have been rejected by the reviewers. And this is something that is very often also neglected by people to document, and it's a hugely important piece of information to keep track of those. And then basically you use various tools and forms of human review to iterate over this process until you have a level of noise that you find acceptable for your use case, and you spit out the final mappings, positive and negative, out on the other end. So that's just like to put all of these into one big process.